Well, good evening, everyone. It's now 5 p.m. local time. I might make a start on this evening's lectures. Thanks to everyone who came this evening. I can appreciate that it is difficult to continue to bring yourself to these lectures, and your participation and attendance is very much appreciated. So thank you all for being here. The plan for this evening, hopefully, is to finish off Unit 7 here and make a start on Unit 8. And hopefully by the end of tonight, we will have done Taylor series. And so hopefully then after tonight, you will be in a position to complete your assignment 2 for next Thursday, I think it is. So we'll make a start. As always, if you have questions, please feel free to write them in the chat and I'll endeavor to answer them as best I can when an opportunity arises. All right, so you may recall that at the end of last lecture, we were dealing, well, I think we left at this theorem here. So you might remember that we talked about the definition of a critical point, and we also talked about the definition of local maximums and local minimums. For 9 times out of 10, what you're really interested in real life are the local maximums and minimums. And so you might wonder why would you be interested in critical points? And the answer really is this theorem here, which says that any local maximum or minimum of a particular function f has to arise as a critical point of that function f. So remember, the definition of a critical point is that either the derivative is 0 or the derivative fails to exist. So the proof of this result is, well, let's assume to start off with that you have a local maximum. Now, if you have a local maximum, then by definition, that means that the function is not, it's never going to exceed the value of the function at the particular point of the local maximum. Now, remember, critical point, that means either the derivative is 0 or it fails to exist. If it so happens that the derivative does not exist at this point, then we're done. On the other hand, if it does exist, then that means that this derivative exists. And remember how the derivative is defined. It's defined to be this limit. Now, since this limit exists, it has to be the same as you approach this limit from above and from below. Now, in both of these cases, the numerator is going to be negative. And this is because we're dealing with a local maximum. But this guy on the denominator, this is either positive or negative, depending on what side of A you're on. So if you work this through carefully, you'll find that if you're approaching this limit from above, you get something that's non-positive. But if you approach from below, you get something non-negative. These two limits both exist and have to be the same thing because we're now assuming that the derivative exists. The only number that is both non-positive and non-negative is 0. So we conclude that the derivative is 0, and so that means if either the derivative does exist or it does not exist, we have to be at a critical point. So this is a tool here that really helps us to approach the problem of finding local maximums and local minimums of a particular function. Now, this gives us a sort of rough idea about where our local extrema should be. They should be critical points. But now the question is, if we've got a critical point, how can we tell whether it's a local maximum or a local minimum? And this is where we start talking about something called the first derivative test. So really what we've got in mind here is we've got a critical point of a particular function. We want to know whether it's a maximum or a minimum, and we're going to do that by looking at the first derivative. So to start, let's suppose we've got a function f, which is continuous on a closed interval, and let's say that it's differentiable on the corresponding open interval. Now, I'm going to pick a point C that's in this open interval, and I'm going to see under what circumstances I can say that this C is either a local maximum or a local minimum. Let's see under what circumstances we can guarantee that this point is a local maximum. Well, if it so happens that the derivative is positive before c and happens to be negative after c, then your function actually has to have a local maximum at c. Maybe that's not too surprising, but nevertheless, this is an important observation, and so we'll state it as a theorem just to make sure you know just how important this is. Of course, the same is true in reverse. If, on the other hand, the derivative is negative before c and happens to be positive after c, then you're dealing with a local minimum. Now, there is a brief proof of this result that we're going to go through, and it relies on a piece of information we actually already dealt with. Namely, we know that if a derivative is positive on an interval, then the function has to be increasing on that interval. On the other hand, if the derivative is negative, the function has to be decreasing on that same interval. So this is the main technical tool we'll use to do this proof. Hopefully you can appreciate that the proof of these two results are basically identical. So we're just going to do one of them. Hopefully no one's terribly upset about that. So let's say we're in the situation of this first one here. Let's suppose that the derivative is positive on this interval here. Well, as I said before, since the derivative is positive, that means that, well, we've got, if this is a, b, and c here, if the derivative is positive on this interval, then we have to be increasing. So that means the value of the function at this point here has to dominate all of the other values over here. That's just exactly what it means for the function to be increasing. On the other hand, we know that it's decreasing afterwards. So again, this value has to dominate everything that comes afterwards. So since f is decreasing, we find that f of x is less than or equal to f of c for all x in this interval. But if you combine the facts that, well, this estimate holds for all x before c, and it also holds for all x after c, and that's the exact definition of a local maximum. So that's more or less the entire proof of that. Again, it seems obvious, and it more or less is, but it's important to note that we did need the technical tool here. The fact that the mean value theorem tells us that functions with positive derivatives are increasing, functions with negative derivatives are decreasing. So this is the first derivative test. Now, at least when I was learning all of this stuff for the first time, it wasn't actually the first derivative test I was originally taught that told me whether or not a critical point was a maximum or a minimum. I was initially taught the second derivative test, and maybe you guys are more familiar with the second derivative test as well. So the second derivative test, we're in the same situation as before. We want to determine whether or not a critical point we've got is a local maximum or whether it's a local minimum. As the name suggests, for this test, we need information about the second derivative. So we're going to again suppose that we've got a continuous function on a closed interval. This time, we're going to assume that the second derivative exists everywhere. Sorry, no. For this test, we actually only need to assume that f prime prime exists and is continuous at a specific point. So what this means is that we need f prime to exist at C and in a neighborhood, potentially small neighborhood of C, and f prime prime must be continuous here. So this is just a slight elaboration of what I'm saying with this sentence there. So we need it to exist at C, we need it to exist close to C, and we need that to be continuous. All right, what does the test say? Well, if we happen to be at a critical point, let's suppose that the derivative is 0, and let's also suppose that the second derivative is negative at this point. Then if we happen to be in that situation, then we can conclude that C must be a local maximum of F. Of course, the exact same thing holds in reverse. On the other hand, if your derivative is 0 and your second derivative is positive, then you have to be a local minimum of F. Now, even though this is apparently a different test to the first derivative test, the proof of the second derivative test relies crucially on the first derivative test. So let's see how that works out. Again, I'm going to hope that you'll be convinced that proving 1 is enough. As soon as I prove 1, I can just use the exact same techniques in reverse, putting minus signs in appropriate places to get the proof of 2. So I'm going to stick with the proof of 1 for the moment. So let's prove 1. Let's suppose that the second derivative is negative. Now, this is why we need continuity. This is another one of those things which is obvious to some extent, but needs to be stated carefully. If the second derivative is negative at C, then it's also negative for values of x which are close to C. So what do I mean by this? Well, if I do a graph, let's put x on the x-axis and let's put the second derivative on the y-axis. Let's say I've got B, A, and C here. The fact that the second derivative is negative here, well, that's great, but because the second derivative is also negative and continuous, that means it also has to stay negative for some values of x which are quite close to C. If the second derivative weren't continuous, we could have something like this. Of course, the second derivative is continuous by assumption, so that can't happen. It's negative here, so it has to be negative nearby as well. Okay, hopefully all that makes sense. So what's the deal now? We've got a point where the first derivative is 0, and we also know that the second derivative is negative at C and close to C. What can be done here? Well, since the second derivative is negative, remember what the mean value theorem tells us. If the derivative is negative, then the original function has to be decreasing. This time, we know that the second derivative is negative, so the first derivative has to be decreasing. So we know that there is an interval of C on which the function f prime is actually decreasing. So this is the usual positive derivative implies increasing, negative derivative implies decreasing, except we're not applying it to f and f prime, we're applying it to f prime and f prime prime. So hopefully that's not too much of a technical obstacle for you. Right, so we now have that f prime, so let's graph this now. F prime is a decreasing function. However, we also know that f prime is 0 here. In order for the function f prime to be decreasing, it has to be positive over here, has to hit 0 at C, and has to be negative past C. But this is great because this is exactly the situation we're in, so that we can apply the first derivative test. Because the first derivative test says that if your first derivative is positive before, and if it's negative afterwards, then you have to be at local maximum of the function f. So this is the proof of point 1 of this second derivative test. As I said before, point 2 is almost, the proof of point 2 is almost identical. All right. Are there any questions on that? I'll just give a brief pause there. All right, maybe that's all straightforward. Okay, thanks very much, Zhao Wang. Rightio, so these are the basic tools you need when you're trying to do optimization. Now, I want to take a brief amount of time to talk about optimization in Mathematica. In terms of optimizing functions in Mathematica, I suppose it's not really as it's not as great as I would like it to be. What do I mean by that? Well, I did a bit of mucking around in Mathematica for you here to illustrate what happens when you try and do optimization with Mathematica. All right, let's have a look at this first, these first two lines here. So that the code I was using, the command that Mathematica likes is this find maximum, find minimum function. So it's a bit misleading because find maximum and find minimum, basically what that means is finds the closest local maximum, finds the closest local minimum. So what's going on here? Well, in this first line, I was looking at the function f of x equals 1 on 1 plus x squared. And I wanted Mathematica to find a maximum. How did I do that? Well, I told it that I was looking to find a maximum in x. So again, if you define a function with multiple variables, you need to specify what you're maximizing over. And this number here, this number is sort of a starting position. So when you put this command in Mathematica, what you're really telling it is that I want you, Mathematica, I want you to find a local maximum of this function, and I want you to find a local maximum close to the number 5. Or at least that's where I want you to start looking. I want you to start looking at the number 5 and find me a local maximum from there. Now, what's really nice about this function is that x equals 0 is the unique maximum. This is fairly easy to demonstrate using either the first or the second derivative test. You just differentiate, you can find that x equals 0 is the unique maximum. But interestingly enough, Mathematica doesn't actually find that for you. It says that the value of x, which gives a local maximum, is this number here, minus 1.40789 times 10 to the minus 15. What's going on here? Is Mathematica wrong? Well, Mathematica is not wrong if you understand what it's telling you. You told it to start at 5, and so what it does is sort of move sequentially closer to what it thinks is a local maximum. It never actually arrives at the point 0. And that's why it goes on for a very long time. It gets very, very close, which is why you have this 10 to the minus 15 term here. That's very, very small, but it doesn't actually give you the exact answer you want. So that's a bit of a shame. So Mathematica is fine as long as you know what it's telling you. As another fun thing I tried, I was looking at the function. So that was the first two lines here. Let's have a look at the next two lines. I was looking at the function cosine of x. So you may recall that cosine of x looks like this. So that's 2 pi, and that's pi down there. This is pi on 2. So what's going on? I'm saying I want to look at the function cosine of x, and Mathematica, what I want you to do is find me a local minimum of this function. And I want you to do it by starting at the point 0. Now, if you do this, Mathematica gets quite confused because Mathematica, in this command, Mathematica actually computes the derivative here and says, well, the derivative is 0, so I don't know what to do. Because if you think about how Mathematica might try and find these maximums, it really what it wants to do is compute the derivative and travel either left or right, depending on whether the derivative is positive or negative. But I'm telling Mathematica to start at a point where the derivative is already 0. And so it gets confused. So it says, well, if you want me to find a minimum, the best I can give you is the same point that you started off with, the point x equals 0. But it realizes it's not really doing a good job there because it says, well, the reason I couldn't do it is because you told me to start in a stupid place. You told me to start with a gradient of 0, and I can't do anything with that. So I want you to know that even though I gave you an answer here, it may not actually be a minimum. And that's indeed the case. This point here is actually a local maximum. So yes, be careful with that. Okay, so that means that when we're trying to find minimums of this function cosine, we shouldn't really start at 0. So instead, I had a look at what happens if you do it at 0.5. Let's probably around there somewhere. Well, now it can actually work. It tells me that, well, it thinks that a local minimum is going to occur at x equals 3.14159. Of course, we recognize that as an approximation to pi. That's great. Interestingly enough, it'll find the same value if you start at 0.5, because 5 is less than 2 pi. Let's say that 5 is around here somewhere. But what's going on here? Find minimum of the cosine function. This time I want to start at x equals 10. Now that's interesting because 10 is 10 is a while away. I think it's around here somewhere. And this time it finds 9.42478 as a number. This number is approximately 3 pi. So when we start all the way over at 10, it's actually finding the local minimum all the way over there. So this is the sort of fun you can have when you're trying to do optimization with Mathematica. And if you're going to do it in real life, I would urge lots of caution when you're doing this. It's always, well, it can quite often be challenging to optimize numerically. Okay, now we've seen how Mathematica can do it. Let's now have a look at how we can do it without using Mathematica. Before we do that, we've got a question/comment. So just give me a second to read this. That's an interesting question. So Kai has a question about why numerical optimization methods are such a hot topic in current research. I'm not an expert, but the best answer I can give you off the top of my head is twofold. One of them is more or less exactly what you suggested. They really want to make it run as efficiently as possible. When you're dealing with data science and machine learning, you've got huge amounts of data that you need to optimize, and these really clunky sort of Newtonian methods take a lot of time, and Newton's method really can't do you any justice. It won't give you a good answer in a reasonable amount of time. So people need to come up with cleverer ways of actually constructing maximums and minimums. It's all about efficiency, I would suggest. And my other comment is that it's good to know it's good to have algorithms for optimizing that can overcome some of the obstacles. So for example, we encountered a lot of obstacles with Mathematica here when we were trying to optimize. It's good to have algorithms that can overcome these sorts of issues. So as long as machine learning and artificial intelligence is a thing, I would suggest that, well, those things are almost synonymous with optimization. And as long as people are interested in those topics, they'll necessarily be interested in finding new ways of optimizing things. I hope that answers your question. As I said, I'm not an expert, but I'm happy to discuss it further with you later on if you wish. Right. Okay. So we've talked briefly about how computers can deal with this. Let's see how we can do this by hand. So I've got a question for you. Consider the function f, which takes as input a real number and as output spits a real number. Let's say the function is given by 2x cubed plus 3x squared minus 12x plus 4. Find all the local maximums, find all the local minimums. Well, with these sorts of things, it's always good to take derivatives where we can. If we just compute using all the rules that we've established previously, we find that the first derivative is 6x squared plus 6x minus 12. I think I did that right. And the second derivative would be 12x plus 6. So this means that not only have we computed the first and second derivatives, but it's also good to notice that these functions exist everywhere and they're continuous. So that means that in our quest to discover maximums and minimums, we are allowed to use the first and second derivative tests. Now, since the first derivative exists everywhere, the only critical points are going to be the points where the derivative is 0. Because remember, critical points are where the derivative is 0 or where the derivative does not exist. The derivative exists everywhere, so the critical points are precisely those points where the derivative is 0. So if we solve this problem here, 6x squared plus 6x minus 12 equals 0, we find exactly two solutions, x equals minus 2 and x equals 1. I won't get into the details of how I got those. You can either complete the square, that's a fairly standard technique, or you can just use the quadratic formula to work out what the solutions are immediately. In any case, two solutions, x equals minus 2 and x equals 1. And yes, Casey, these are precisely the roots of the equation. So when I say find the roots of a particular function, that's defined to be find all the points where the function is 0. So yes, these are the roots of the equation. And okay, now remember, all of the local extremas have to be critical points. So therefore, these are the only possibilities for local maximums and local minimums. Let's try and use the second derivative test to determine whether or not these guys are maximums or minimums. Well, at the first of these, minus 2, the second derivative is negative. So remember, the second derivative is 12x plus 6. If x is minus 2, that's going to be minus 18, I think. So that's negative. So that means that this critical point actually has to be a local maximum. And when you're doing these problems, it's good manners to tell me what the actual value of the function is at that point, because, well, this is the maximizing number. F of minus 2 is going to be 24. What about the other one? Well, if we compute, we find that the second derivative is actually positive this time. So this critical point has to be a local minimum. And again, good manners to actually compute the value of the function at this supposed minimum. So this is actually all we need to do, because remember, this is very important. All of the local maximums and minimums, they have to be critical points. We found only two critical points. There are only two critical points. And we saw that one of them was a maximum and the other was a minimum. And so that's it, we're done. That's the whole question there. Right, so this is this question here. Now, the next theorem that we're dealing with is quite an interesting one, because it says that if you've got a function that goes from a closed interval into R, this is very important for this theorem, so I'll just stress this. This interval has to be closed, and A cannot be infinity, B cannot be infinity. This has to be an honest closed interval for this theorem to work. If you've got a function from when I say that both of these guys are not infinity, that another way of saying that mathematically is by saying that this interval is compact. I'll leave that aside for the moment. So if you've got this continuous function on this closed non-infinite interval, then f is always going to have a global maximum and it is always going to have a global minimum. And what's so important is that these maximums and minimums are actually achieved. So why is this so important? Well, let's say you had a function defined on the interval -1 up to 1 that looked, something like this. On this open interval, there is sort of like a maximal value here. It's whatever this value is over here, but it's not actually achieved by anything on this interval. However, if you change the interval to be the closed interval, then yes, the function is actually going to achieve its maximum. because this time the maximum is going to be on the boundary. So this theorem here is called the extreme value theorem, so called because it tells us that any function on an appropriate interval that's continuous, it always achieves its extremal values. So this is the extreme value theorem. This is good to know because it means that if you're ever asked to optimize a function that's continuous and defined on a closed interval, you'll know that there is actually an answer. For some of these optimization problems, they don't actually have maximums. They don't actually have minimums. But in this case, there will always be a maximum and there will always be a minimum. And this is another fun theorem. A lot of in many of the exams I've written, I've seen students use this theorem without really stating it, and it hadn't been taught. So to overcome that, I'm just giving you this theorem right now. Let's suppose that you've got a function which is differentiable on an open interval, and let's say it has only one critical point. If you have only one critical point, then the global behavior of this function is basically determined by the behavior of this function at that critical point. If the critical point is a local minimum, then it actually has to be the global minimum of this function. On the other hand, if the critical point is a local maximum, it must be a global maximum. And this time, the function still works even if one of your numbers are plus or minus infinity. So this is pretty nice. All right, so let's have a look at this, all these theorems at work. Another question. Let's say that we've got a function, f of x equals x cubed minus 3x squared plus 1, and we're looking at this function on the closed interval. So because this function is a polynomial, it's continuous, and we're looking at it on a closed interval, so the extreme value theorem tells us that actually there does have to be a global maximum and a global minimum. This isn't a trick question. It's asking for a global maximum, it's asking for a global minimum, and they have to actually exist. Okay? How do we find global maximums and global minimums? Well, remember, global maximums are local maximums, and global minimums have to be local minimums, and all local extrema have to be critical points. So once again, the first thing we should do is try and find the critical points. You find critical points by looking at the derivative and setting equal to 0. In this case, the only critical points are 0 and 2. I think I should be a bit careful here. The only interior critical points are x equals 0 and 2. Because remember, critical points are where the derivative is 0 or where the derivative does not exist. Since we're only looking at this function on the closed interval, technically speaking, the function is not actually differentiable at those endpoints, so they're critical points as well. So now that we know that the only interior critical points are 0 and 2, and the only other critical points are the boundary points, namely -1/2 and 4, in order to find the global maximum and global minimum, we simply have to check the value of the function at these 4 points. So this is what I'm saying here. Therefore, the global maximums and minimums have to occur at one of these 4 points. And remember again, the reason I've included -1/2 and 4 here are because those are the endpoints of this particular interval. So now that we've got 4 candidates, we simply need to test them all out. So I won't go through these computations in great detail, but we find that if we plug in 0, the output is 1. If the input is 2, the output is -3. If the input is 1/2, the output is 1/8. And if the input is 4, then the output is 17. This is the biggest value here, and this is the smallest. So that means this one has to be the global maximum, and this one has to be the global minimum. So this is a good practical example of how you find global maximums and minimums of functions when you're dealing with the function as being restricted to a closed interval. So that's lots of fun. This actually brings us to the end of the optimization component of section 7. I'll again invite questions very briefly, because I realize some people don't like asking questions. All right, so I'll move on with the next part of this unit. Ordinary differential equations. This is a very, very big topic, and it is a bit of a shame that we can't do more of it in this particular class, because it is a very important subject. But hopefully we'll give you a bit of a taste of how much fun this particular unit can be. So basic ordinary differential equations. The reason ordinary differential equations, I'll get to your question in a second, Casey. We're going to be dealing with a whole bunch of them. So the reason differential equations are so important is because in a lot of situations in real life, we've got a function that we want to study, but we don't actually know what it is explicitly. Instead, the function is only defined implicitly through these things called differential equations. So you don't explicitly write down what the function is. Instead, the only information you're given off the bat is some information about how a function is changing with respect to its input variables. So what that means is that you don't have something like f of x equals, x squared plus 1. This is a very explicit way of describing a function. Instead, you might describe the function more implicitly by specifying what its derivatives look like. You might specify something like f prime of x equals something, and this could be a very implicit way of describing the function. Now, so in this particular course, where we'll only be dealing with ordinary differential equations, and even that we won't be doing much to it, but it's very important to note that there are, well, sorry, let me say what I mean by ordinary differential equations. This is where the functions that we're dealing with only depend on one variable. So that's like f of x. So if the unknown function only depends on a single variable, usually this variable would be time or a single spatial variable. In that case, we're dealing with ordinary differential equations. However, if you're dealing with functions of time as well as multiple other variables, if there's more than two variables in there and you don't know what that function is, and the function is specified by specifying how its derivatives behave, and that you would call that a partial differential equation. Now, we'll only be dealing with ordinary differential equations in this course because they're much easier, and we're not doing much on ordinary differential equations anyway. But it is very important to note that partial differential equations occur a lot in real life as well. So hopefully you'll encounter these at some point down the track in your mathematical studies, but unfortunately we won't be talking about them this semester. All right, so now something else, something along the lines of what Casey was just asking, the order of a differential equation. If you have a differential equation that specifies how its derivatives are behaving, the order of that differential equation is the order of the highest derivative that appears in the equation. So for example, the equation f prime of x equals, let's say, f of x squared. This is a first order ODE. It's an ODE because only one variable appears, and it's first order because there's only one derivative here. On the other hand, something like f prime prime of x equals pi, that's a second order ODE because there's only one spatial variable and we've got two derivatives to worry about. So this is a basic notation and sort of phraseology that I'll be using when going through this particular section. Okay, one example that comes up a lot of ordinary differential equations is when you're modeling populations. So let's say that you've got some population. It could be the amount of a chemical in your body. It could be an actual population of animals or people. But let's say you've got some population. Now, the basic model of a population is that its growth at any particular time is going to be proportional to the population itself. So this is what I'm saying here. We're assuming that the change of the population at any given time is actually proportional to the population itself. If this is K is the constant of, I hope I get this word right, proportionality, I think that's a word. K is the constant of proportionality. And that means that the way that you describe what the population is, you do that through this differential equation. You say that the derivative of the population in time at any given time is the same as the population itself times by this proportionality constant. So this is one way in which you specify a function that you're interested in, namely p of t, through describing how its derivatives behave. Now, I'm sure maybe a lot of you know what the solution to this differential equation is. It's called exponential growth because the solution of this particular equation is exactly the exponential function. So this is the general solution of that particular equation there. And while you may know what that is, it's also sometimes good to give really qualitative descriptions of solutions of this equation. If k is strictly positive, then that means that the population is actually growing, exponential growth. On the other hand, if k is negative, then your population is decreasing. And in fact, you've got exponential decay. So that's the case when you're dealing with radioactive material. If you've got radioactive material, the amount of material that gets shed off is actually proportional to the amount of material already there. On the other hand, if k equals 0, then the population is not changing at all. And so you wouldn't really call that exponential. You would just call that no population growth at all. So this is an example of a differential equation, a very real life one. Now I'm just going to chuck you straight in the deep end and give you a very abstract differential equation. So, but the good news is I'm not just giving you the differential equation, I'm also giving you the solution. And all this question asks you to do is verify that this function does actually solve this differential equation. So the differential equation we're dealing with is that of, let's say we've got some function y of x. And what I want, I'm not going to define this function explicitly. Instead, I'm just going to tell you that the derivative of y at any given x is the same as x times y evaluated at that same x. Now, 9 times out of 10, I would just give you this equation and ask you to solve it. But this time I actually gave you a suggested solution. I suggest that the solution should be a times the exponential function of x squared divided by 2. And I claim that this should be a solution for any real constant a. The question here is, I want you to check that. Okay. How does that go down? Well, it's basically just a case of putting this expression here and hoping everything works out. Let's evaluate the left-hand side. Well, if y equals a times the exponential function of x squared on 2, I need to differentiate that. How do I differentiate that? Well, this is the chain rule, and we also have to remember how the exponential function differentiates. Because remember, if you differentiate this function, the derivative of the exponential function is just itself, but the chain rule tells us that we've also got to multiply by the derivative of what's inside the exponential. And this is precisely x times e to the x squared on 2. Remember, of course, we had another constant out the front of everything. So that's the left-hand side. On the other hand, the right-hand side simply asks you to multiply that function by x. So a times e to the x squared on 2 times x, that's exactly that. So both the left-hand side and the right-hand side are the same. So we've got a solution to our differential equation. Now something that's interesting here is this constant a here. Maybe you might find it surprising that we can find that not only do we have a solution, but we actually have infinitely many solutions. You pick any a, and I'll find a solution of this equation here. This is actually a general phenomenon that occurs quite regularly, namely that solutions to differential equations quite often have arbitrary constants flying around. And this is an important point that we need to make here. If I give you an ordinary differential equation, and I ask you to solve that differential equation, what I really mean by that is I want you to find all possible solutions. And this includes those ones with, this basically means you need to keep in mind all of those arbitrary constants that could be flying around. So as a general rule, this is quite often the case, not always the case, but is quite often the case, that if you've got an ODE that only has one function and the differential equation is a first order one, so we talked about what that means before. Let's say you've got a first order ODE of only one function, then the solution quite often has a single arbitrary constant that must be accounted for. On the other hand, if your differential equation is higher order, this usually has two arbitrary constants. So this is very important when you're answering questions. When you're told to solve a differential equation, that means find all possible solutions. Okay, might just start this question here. This might be the last thing we do before we have a break for 10 minutes. Question: solve the ODE y prime of x equals x squared. So this is a first order ODE of one function. So that means we expect there to be one arbitrary constant flying around. Now, there is an obvious solution to this. The obvious solution is x cubed on 3, because I happen to remember that the derivative of this function is exactly that. But perhaps there are more solutions. You know, we've said that there's probably going to be one arbitrary constant lying around here that we need to account for. So how do we account for that? Well, it turns out that in this case, the general solution is yx equals x cubed on 3 plus c for some arbitrary real constant c. Now remember, when I suggested up here that to solve a differential equation, you need to find all possible solutions. Now, I claim that yx equals x cubed on 3 plus an arbitrary constant c is actually all of the solutions. Now, this is a question I'd like to leave you with over the break. Maybe you can think about it or someone can answer immediately. how do I know that this is actually all the solutions? So I'll leave that there. If you think you've got an answer, maybe you could put the answer, maybe you could write the chat. So KC has just asked for clarification on what I'm asking here. So I suggested that to solve a differential equation, you have to find all possible solutions. Now, I'm claiming that this is actually all of the solutions. Y equals X, any solution of this particular equation looks like this. How do I know I've got all of them? How do I know there's not some other crazy function that solves this problem here? This is the question I'd like you to think about over the break. So hope you have fun with that. I look forward to seeing your answers shortly. Have a good break. I'll see you around. Welcome back, everyone. So yes, we did have a couple of answers in the chat. The first comment suggests that nothing else can differentiate to be x squared, except for maybe that and a constant, and that is more or less true. But the explanation for that was almost given by Zhao Wang. I think maybe there's possibly some notational inconsistencies in your work, but more or less that's the exact idea. Let's pull back a second. So how do we know, the question was, how do we know that adding C is the only thing you can do to a solution to get another solution? And the way we see that is as follows. If y1 and y2 were both solutions, then let's differentiate the difference. Let's use Newton's notation. y1 dash of x minus y2 dash of x. Well, we remember our differentiation laws. This is just equal to y1 dash of x minus y2 dash of x. But we're assuming these both solve this particular equation here. And so what that means is that we get x squared minus x squared equals 0. So we've got a function. Oh, sorry, that's a bit silly. Derivative on the outside of that bracket. We've now got a function y1 minus y2 whose derivative is 0. Remember, there was a theorem we did a while ago, which was basically just a consequence of the mean value theorem, that if you've got a function whose derivative is 0, then this has to be constant. So that, excuse me. So that means as soon as you found one solution, which we have, we know that a solution is x cubed on 3. As soon as we've found one solution, all of the other solutions have to be that same function plus some constant. So that's why these are all of the solutions there. So I hope that makes sense. Basically, the reason that plus c is here, and we know that that's all of the solutions, is that the constant functions are the only functions whose derivatives are constant. So it's the only function you can add for free without changing the derivative. So that's essentially why we've found all of the solutions here. So this was a first order equation with only one function. The extra constants that come flying out when you increase the order of the equation and increase the number of functions you're dealing with, that starts to get pretty big quite quickly. And you may have noticed that in order to specify what these arbitrary constants are, you need to specify initial conditions. So what I'll say here is that initial conditions are typically the things that you use to specify what your arbitrary constants are. So what's the question here that we're dealing with? Well, we're throwing apples for whatever reason. We're going to keep track of the location of these apples. We're going to let x of t be its sort of horizontal displacement, and we're going to let y of t be its vertical displacement. We're going to assume that it's horizontal and vertical displacement. They're both set to 0 initially. And we're also going to specify what's the first derivative of both the horizontal and the vertical displacements are. Now, the question is, actually find an expression. Find what this function is, x of t, comma, y of t. How do we go about doing that? Well, I think what is perhaps quite tricky about this question is that there isn't actually a differential equation lying here anywhere. I've only told you initial conditions. I haven't actually given you a differential equation. So I think what's tricky about this question is that you have to make your own differential equation up, and you have to do it using physics. So for that reason, this becomes somewhat of a rather tricky question. And the way we do it is by noting that, well, in physics, if we throw something, we're going to assume that air resistance is negligible, and we're going to assume that the only force acting on these apples is gravity. So that means that there's not going to be any horizontal acceleration. We're assuming that wind and air resistance is negligible. And we're going to assume that the only vertical force is the one pulling it back down to Earth, the gravity. Gravity typically means that its vertical acceleration is this minus 9.81. This is, you can kind of think as this is like a gravity constant. You may have seen this number before. So if you don't know where these equations come from, don't worry too much. I'm just pulling this out for the moment. Okay, so these are the ODEs that we're trying to solve. They're second order, and there are two of them. So let's get to it. Integrating once. Now, we haven't actually talked about integrating yet. And so when I say integrating, what I mean by that roughly is undoing one derivative. So integrating once. What do I mean by that? Well, let's have a look at this x equation. The second derivative is 0. That's what we're saying. Now, as we just said, in order, any function whose derivative is 0 everywhere, that function has to be constant. Now, we're saying that the second derivative of x is 0, which means that its first derivative has to be constant. What is this constant? Well, it has to be the same constant that it is initially. So that means that x prime of 0 has to be u, because that's what the x displacement is initially. Okay, that's the easy one. What about this one? The second derivative of y is minus g. One particular function whose derivative is minus g is minus g times t. So that means that we could use this to be our initial, to be our solution of the y velocity. But the problem is, well, we know there has to be a plus c here, but this plus c has to be equal to v, because we've said that initially the y displacement is v. So the solution of this problem is that guy there. So we've now sort of boiled down, we've turned our second order equations into two first order equations. So now let's integrate once more. Okay, well, the derivative of x is equal to u. And so that means that one particular function that will solve that problem is just multiplying that number by t, because the derivative of ut with respect to t is exactly u. Now remember, we've got a plus c lying around, but that plus c equals 0 because we're specifying that the velocity is initially 0. So that's great. What about the y one? Well, the derivative for y is v minus gt. If we integrate that, find a function whose derivative is v minus gt. Well, that's just a constant, so we can multiply by t, and using our power rules for derivatives, we get g times t squared divided by 2. We've got our plus c's to worry about again, but if we set t equals 0 here, we get that y of 0 is equal to 0, which is exactly what we want in the first place. So this is the solution of this particular ODE there. It basically just boils down to undoing the derivatives. Try and find functions whose derivatives are something instead of working the other way around. So I can appreciate that that might have been a bit of a jump for some of you. So I did want to give an opportunity to ask questions briefly, apart from maybe the physics, because that's not exactly what the emphasis of this course is. I more or less just pulled these equations out of nowhere. So any other questions on that? Yeah, this is an excellent question. Why did I use minus g instead of g? And it's basically how I chose my coordinate system. So y, if I let this be y and x, and the x-axis is the ground, then gravity is actually going down that way, which is why the acceleration is pointing down, which is why the acceleration is negative. If the acceleration was positive, it would just keep going up and up and up, and it would never come back to the ground, which is not terribly realistic, I would suggest. Yes, good question. Right, sweet. I'll move on then. Just before we wrap up the ordinary differential equations unit, yes, I know this was very short indeed. We barely got to do anything with ODEs, but those two examples that we just looked at were situations in which we could actually write down a solution explicitly. It turns out that you can't always do that. So to sort of differentiate between when we can do that and when we can't do that, we talk about solving solutions of ODEs analytically and solving these ODEs numerically. So solving ODEs analytically is what we just did. So it means we actually explicitly wrote down the solution in terms of well understood continuous functions. So there are many of these. Polynomials, I would suggest, are examples of well-known continuous functions. The sine, cosine, and exponential functions, I would say, are pretty well-known examples of functions. And you also are allowed to combine these. If you're able to explicitly write down a solution in terms of these functions, then you say that you have analytically solved your equation. But as I said, this is not always possible. And so when it is not possible, if you want to get a good idea about what the solution of your equation looks like, you really need to resort to more numerical methods. So what this essentially boils down to is telling Mathematica or any other software you choose to use, you're telling it to produce not an exact solution, but telling you, sort of asking, you're asking the software to plot a function, which is supposed to be a good approximation for what the solution actually is. Now, numerical techniques that are used to solve ordinary differential equations, that is a very, very well-researched, well-studied area of mathematics, and there are, in fact, entire courses dedicated to this at UQ. We will not be pursuing this here, but as data science students, I think it would be very important for you to learn some of these numerical methods somewhere along the lines, but unfortunately, it's not going to be now. So sorry about that. I think it is a very important subject, but we're not going to be dealing with it too much here. Okay, now the last thing I wanted to do with Unit 7 this evening was give an application. I made a sort of pessimistic remark recently, suggesting that any mathematician that's employed in the industry, that person's job is going to be to save a particular company money by doing things more efficiently or working out much better ways of doing things. And I wanted to give you a rather elementary taste of what that actually looks like with this final example of this unit. So I really like this question because it's a geometry type question, and I like geometry. So the question is as follows. We've got a farmer who has 400 meters of fencing, and the idea is he's meant to use that fencing to produce a rectangular paddock for grazing. What is the maximal area of that particular paddock? Now, I'm sure that you can work out immediately what the answer to this is. Since I'm telling you that it's rectangular, you know that the answer is, well, surely a square is the best way to arrange it. And indeed, that is the case. But I want to show you how you can come to that conclusion using the optimization techniques that we were looking at earlier this evening. So to set this up, I'm going to introduce these parameters here, x and y, which actually describe the length of the rectangle in meters. Okay, so what are the rules here? Well, I'm trying to maximize area. The area of a rectangle is simply the length of its base times the length of its height, and that is precisely x times y. However, we've got more information here. We know that we're only allowed to use 400 meters of fencing. 400 meters is the perimeter. So that means we've got this constraint here. I know that the perimeter, which can be found by taking 2 times the base plus 2 times the height, that has to be 400 meters. So let's now try and write this as an optimization problem. Well, if I rearrange this equation, I find that x has to be equal to 200, y has to be the same as 200 minus x. So if I plug that value of y into there, I find that for any given length of the base, the area is going to be x times 200 minus x. This is the thing that I now want to optimize. How do I do that? Well, I need to find the critical points. How do I do that? I take the derivative. Turns out that the derivative of this function is 200 minus 2x. And the second derivative is just minus 2 everywhere. And so that means that we've only got one critical point. And since we've only got one critical point and the second derivative is negative, that means that this local maximum actually has to be a global maximum. And of course, this would be completely unsurprising to you because, well, then the optimal shape here is precisely the square. The square has length 100 meters, and the area, of course, is going to be 100 meters squared, which is 10,000 meters squared. So that's the answer to that particular problem. Now, before we move on, I'm going to ask you a bit of an open-ended question that I would like you to respond in the chat if you could. Now, I'll just preamble this by saying that there is really no correct answer to what I'm about to ask you, but I am interested in your thoughts. What is the domain of this function here? You may notice that I didn't really specify a domain here. So what should I do for this domain? Do I need to specify it? Does it matter what the domain is? I'm quite interested to see how you react to that particular question. So seems like a lot of people are suggesting that the answer should be that a suitable choice of domain would be values of x between 0 and 400. Now, I think that might be a little bit off. I think really what you mean by that is 0 to 200. Because remember, x is just the length of one of the sides. And remember, I'm insisting that I've got a rectangle here. Yeah, so I've got... Yeah, so I mean, one possible answer I think is 0 to 200. Perhaps that's the most natural domain for this problem. But interestingly enough, I would actually suggest to you that, well, realistically, we need x between 0 and 200. But for this particular question, it doesn't really matter. Because if you allow x to be outside of those parameters, this area is going to be negative. And so when you're trying to find a positive maximum of something, you really have to ignore all of the negative values anyway. So the fact that that's not a physically realistic solution, that comes out in the wash anyway, and everything works out, and we're all happy. So yes, that was sort of somewhat of a trick question, but as I said, there weren't really correct answers to that one. Now, the very last thing I wanted to talk to you about in section 7 is not something that's really accessible at all, but I thought that this was a really interesting question. Let's now suppose that we've got a farmer, same problem as before, 400 meters of fencing, he gets to fence off a paddock, except this time I'm not going to insist that the area he's fencing off, I'm not insisting that that's going to be a rectangle. It can be any shape you want. What is the maximal area of the paddock? Or perhaps maybe a more general question, what is the best shape of this paddock? Now, I'm sure you all know what the answer to this is, but just for my sanity, please just quickly type in the answer. Circle, yep. Okay, I presume no one else is going to answer that. Yes, the answer is a circle, but now my question is why? How could you prove to me that the circle is the best choice here? How do we know that? I won't ask you to put that in the chat because it is actually a very, very it's a fairly difficult question to answer. At least it's not something that we can answer using the techniques in this section. But I just wanted to leave Unit 7 here to let you think about how you might answer this question and what sort of techniques you need to develop, and hopefully to convince you that there's a lot more to the story of optimization that we can't cover this semester, but hopefully you'll be interested to learn the answer at some point down the track. So yes, unfortunately, I have to leave you with techniques well beyond this subject. I found that interesting. Maybe you find this idea interesting as well. So that's section 7. I'll now change slides to my section 8 slides. I'll leave about a minute or so while I do that for any other comments or questions you might have. So I've got a question, do we need section 8 for assignment 2? And yes, you do need that. I realize I don't think that you only suggested you would need section 8 when at the very start of the semester, but it turns out that you do. And the hope is that after tonight, you will have all of the information you need to complete your assignment. In particular, what you need to understand what Taylor series are in order to do your assignment. And as I said, hopefully you'll be fine with that after we finish the lectures tonight. All right, let's get on with it. So, Unit 8, Linear Approximations and Taylor Series. This section concerns situations in which you have once again, like the ordinary differential equations section, you've got a function, but it might be a very difficult function to deal with. And so you need a way of reducing the information of that function so that you can actually deal with the function. So you approximate the function with these simple objects, hopefully, so that for all intents and purposes, all of the computations you do with the simplified version of the function are good enough approximations to what happens with the original function. Now, the simplest type of approximation you can make is the so-called linear approximation. So in this situation, basically what's going on is you've got a function f of x in this particular graph here, In this particular graph here, the function f of x is given by the green line. So you've got a function. You may know some information about it, maybe you don't, but maybe the function is too difficult to deal with. For whatever reason, you just don't want to deal with the original function. Okay, well, what do you do? If you happen to know what the value of the function is at a point A, and you also happen to know what the derivative of the function is at that point A, what does that tell you? Well, remember, the derivative is exactly the tangent line. So the fact that you know what the function f is and you also know what its derivative is, that tells you what this red line is. This red line is the tangent line. And the hope is that for values of x, especially for those values of x close to A, this tangent line is actually a good approximation of the green line. So graphically, we're simply saying that this green line is close to the red line. In the equation mode, what that means is that this f prime of x is approximately equal to f of a plus the derivative of f evaluated at a times x minus a. So this is the idea of a linear approximation. And the hope is that this tangent line does actually contain enough information to be good to give us good estimates about the original green function so that we can use it in computation. Because in general, I made a typo here. This derivative here should not exist. It's just f of x. F of x is supposed to be close to f of a plus f prime of a times x minus a. All right, let's have a look at an example. Let's say that you've got a population model, P of t, and let's say the model is this number here, that's 14,931,234 times e to the power of 0.002 times t. And let's say that t is simply the number of quarter years since 1981. Now, when doing computations with this, you might not like this population model because for whatever reason, you might not like the exponential function. Let's say you just have an aversion to using the exponential function for whatever reason. What do? Well, let's assume that t is close to 70. Let's say that we're only doing population modeling for p close to 70. Then this linear approximation tells us that this population should be close to p of 70 plus the derivative of p evaluated at 70 times t minus 70, because that's what our linear approximation was telling us. So in order to get an approximation, all we need to do is evaluate these two numbers here. Well, evaluating p of 70 is easy enough. We just have to plug in 70 there. On the other hand, if we compute the derivative, remember how exponentials differentiate? The constant just gets pulled out the front. The 0.002 also goes out the front. And we're just left with e to the power of 0.002 times t. In that case, this formula here becomes exactly that. And if we expand the brackets, we get this approximation here. So that's good. This is a linear approximation that might be useful in real life if for whatever reason we didn't want to deal with the exponential function. Okay. Now that's basically as deep as linear approximations go. But the point of this subsection was to give us insight into how powerful we can make these approximations. And so with that in mind, we move straight on to the thing which you need to do your assignment, Taylor series approximations. So let's suppose that you've got a function f of x. Let's suppose, for the sake of argument, we'll get onto why we might be able to do this later, but let's suppose that the function f of x can be expressed as this particular infinite sum here. So hopefully you all remember what infinite sums are. just one infinite sum. So I've got an infinite sum. We've got, and the point is all of these terms in here are just polynomials. So let's write out the first few terms to see what this looks like. F of x equals C0 plus C1 times x minus a to the power of 1 plus C2 times x minus a to the power of 2 plus C3 times x minus a to the power of 3, and so on. Hopefully you get the pattern here. Let's say that f of x actually looks like this. And let's say we've got these coefficients like that. Now, the interesting thing is that these coefficients can't be just anything. And in fact, what these coefficients are really depends on what the derivatives of f are. So once again, Casey, have asked a question that we're just a couple of minutes away from answering. Yes, Taylor series, Maclaurin series are just special cases of Taylor series when a equals 0. So we'll get to that in a second. So yes, now what's going to happen? I'm going to try and find these coefficients in terms of the original function f. Okay, so remember that f of x equals C0 plus C1 of x minus a plus C2 of x minus a squared, and so on. If I set x equals a here, then I get f of a equals C0, and all of these other terms disappear because I've got C1 times, well, x equals a, so that's 0, plus C2 x minus a, that's still 0, and so on. So we find that C0 has to be the same as f of a. Well, what next? Well, let's differentiate. If we differentiate this equation, what we find is that f prime of x is equal to, well, what happens? The derivative of a constant is 0. The derivative of x is just 1. So we get C1 plus 2C2 times x minus a plus, and at higher order terms, 3 times C3 times x minus a squared. But if I set x equals a here, what I end up with is C1 plus 2 times C2 of, well, x minus a is 0, plus 0, plus 0, and so on. So I find that the first constant is just f of a, and the second constant is just f prime of a. Well, what happens after that? Well, let's have a look at the second derivative. This, well, the C0 term goes away, the C1 term goes away, and we're left with 2 times C2. Might need to remind ourselves what this thing looks like. So the original f of x function was C0 plus C1 times x minus a plus C2 times x minus a squared plus C3 x minus a cubed. If I differentiate twice, these two terms go away. Here, what happens? The 2 comes out the front, and then I've got to multiply by x minus a. But then I've got to differentiate again, and that term goes away. I'm also left with, if I differentiate this twice, I get 3 times 2 times C3 times x minus a, and lots of other terms. And this time, if I plug this in, I get that the second derivative of a is just equal to 2C2. So that means that the C2 number has to be equal to f prime prime of a divided by 2. Now, each time we do this, each number up we go, we get an extra number coming down, and that number is increasing. When we do that, we get precisely this factorial here. So that means that each of these numbers Cn can be found by taking the nth derivative of the function evaluating at a, and then dividing by n factorial. So this means we get this interesting expression here, namely that f of x has to be the same as the infinite sum from n equals 0 up to infinity of the nth derivative of f, evaluated at a, divided by n factorial, and then we've got to multiply by x minus a to the power of n. So what's going on here? I haven't really done anything here. I've just assumed that we have a function that looks like this. And I'm saying that in general, if I have a function which looks like this, then these Cn constants can't just be anything. They have to be these. And so I have this nice expression, which in general says that if I've got f, which can be expressed as an infinite sum of these polynomial terms, then it has to look like this. So with that in mind, we define Taylor series. Let's suppose that you've got a function whose derivatives all exist to arbitrary order at a particular point A. Then when I say the Taylor series of f, what I mean is that is this expression here, the infinite sum of all of these terms, the nth derivative of f evaluated at a, divided by n factorial times x minus a raised to the power of n. And we had a question earlier, and the answer is here. If a equals 0, this is still called a Taylor series, but you could also use the term Maclaurin series. So Maclaurin series means just a Taylor series, except a equals 0. It saves using a couple of words if you just say Maclaurin series instead of saying Taylor series of f evaluated at a. Now, in the last slide, I had this equation here. I didn't just have this, I said that this guy actually equals f of x. But whether or not that's always true is a very subtle question. And the question is, when is it true that a function f, whose derivatives exist to arbitrary order, when is it true that such a function can actually be the same as this infinite series? Because, you know, there's a priori, there's no reason why if I just add all of these things up, I'll end up back with f of x. Why would that be true? Under what circumstances is it true that this series is actually equal to f of x? Now, it turns out that under quite general scenarios, we do actually have that f of x is equal to its own Taylor series. In fact, we have this theorem here. It's a bit of a silly theorem because I'm not really explaining what's going on in here, but I'm saying that if f is good enough, what does good enough mean? Well, we'll touch briefly on that in a second. But if f is good enough, then it does actually equal its own Taylor series, at least if you're close to the point A. So if you pick a point A and pick the Taylor series of f at that point A, and if the original function is good enough, then in fact you're going to have this nice expression for f of x, namely that f of x is equal to its own Taylor series. Now, the maximal number r that you can put here, so r is describing how far away you can get from A so that your Taylor series still equals the function. The maximal value of r you can take is called the radius of convergence. Now, I promise you I'd try to explain what sufficiently well behaved means, and it's technical. I don't really want you to pay too much attention to what's going on here, but really the upshot of all of this is that if you take these derivatives and you evaluate at A, then these terms decay quite quickly. That's about as far as I'm going to say on this particular topic here. But basically what's so great about this course is that we're more or less going to assume from now on that all of the functions that we're ever going to deal with are sufficiently well behaved. So that justifies our use of this theorem here. So for all of the functions we deal with, we are going to have this really nice expression here. Okay, what can we do with this? Well, one thing that's important to note, this is what I was saying here, that we're going to say that unless we specifically tell you otherwise, all of the functions we're going to play with from now on are going to be sufficiently well behaved so that this theorem applies. Now, we've got an infinite sum here, and we haven't talked about convergence of that infinite sum yet. And this is something that we'll aim to address now. Because if it so happens that this guy converges, if we've got that f of x equals this infinite sum, and it actually converges, then what does that mean practically? Why are we bringing this up in a data science course? If it so happens that our function is sufficiently well behaved, and we can write this expression down here, then what that means is that if we cut off this Taylor series at some point, let's say we cut it off at the point k. If we simply cut off a Taylor series at a particular point, then what we end up with, this finite sum, it's actually meant to be a good approximation for your original function f of x. So this is the power of Taylor series. Practically, you can never compute infinite sums, not with computers. However, most of the time you can't compute it with computers. However, computers can deal with finite sums. And if your function is good enough, that means that a finite sum is good enough to give you a really good approximation of the original function that you're dealing with in the first place. Now, the question is, how far away from the point A is this approximation actually valid? So this is that R number again. So I need to work out when this Taylor series actually converges and what this number R is. In practice, you do that with something called the ratio test. And it concerns, it's a test you can use to determine whether or not an infinite sum converges. If you're adding up infinitely many terms, let's say you're adding up this sum n equals 0 up to infinity, then this sum actually converges if this new sequence you take, where you take each element in the sequence and divide it by the one that came just before, if you look at that new sequence and take a limit, you'll find, and if it so happens that this sequence converges to a number less than 1, then you're good to go. This infinite sum does actually converge. Now, this is all interesting, and I promise that soon we'll have a look at actually applying all of this, so hopefully you can become grounded with what all of this actually means. So the way we're going to get familiar with all of these notions of convergence of Taylor series is with a good example. So let's have a look at an example. The first example we're going to look at is a nice function, f of x equals log of x. And we're going to look at the Taylor series about the point x equals 1, and we're going to find its radius of convergence. I think this is a great question to start off with, because, well, the logarithm function, it's quite difficult to define, and it's really difficult to work out what it actually looks like. Finding the Taylor series can actually help us to work out what the original logarithm function actually looks like. All right, let's get started. Now remember, the Taylor series formula we had was the sum from n equals 0 up to infinity of the nth derivative of your function evaluated at the point you're interested in this case 1. We've got to divide by n factorial, and we've got to multiply by x minus a, which in this case is 1. and I've got to raise it to the power of n. Now, the upshot of me writing this down is to convince you that in order to work out what the Taylor series is, we really need to work out what all of these derivatives are. Okay, well, let's just differentiate the logarithm function and see what we get. We actually proved a while ago that the derivative of the logarithm function is just 1 divided by x. So that's great. What happens if you keep differentiating? Well, you just use the power laws that we talked about a while ago. The derivative of 1 divided by x is minus 1 on x squared. So we get a minus 1 out the front. But now that we've got a 2 down the bottom, if we differentiate again, that minus sign cancels out, that 2 goes out the front, and the 2 down the bottom becomes minus 2 minus 1, which becomes a minus 3. So we keep differentiating, and in this way, we get a general rule, namely that the nth derivative of f, evaluated at the point x equals 1, that's equal to minus 1 to the power of n minus 1. So we introduce that to account for the fact that all of our signs are going from plus and minus and so on. And we've got to multiply by n minus 1 factorial. This is accounting for the fact that every time we differentiate, we get another power coming out the front. So this is the general rule for the derivative. But since we've evaluated that, we now know what the Taylor series is. It's minus 1, so we're summing from n equals 1 to infinity of minus 1 to the power of n minus 1 divided by n times x minus 1 to the power of n. So quick question for the audience. In the original formula for the Taylor series, I started my sequence at 0. Why have I started it at 1 here? Have I left something out? What's going on? So I've got one suggestion here. Undefined at 0. So while it's true that the logarithm function ln of x is undefined when x equals 0, I'm actually talking about n equals 0 here. So n is just a number that I use to keep track of the terms I'm adding up in this particular sequence. So I guess I'll just give you the answer. The reason I'm allowed to start my sum at n equals 1 instead of at n equals 0 as usual is because the n equals 0 term, the very first thing I'm adding up, remember the things I'm adding up are the nth derivative evaluated at 1 times x minus 1 to the n divided by n factorial. But when n equals 0, what happens here? Well, all these n's become 0. By convention, 0 factorial is just 1. F of 0 of 1, well, that means I don't take any derivatives. So I just evaluate the original function, and I get 0 times x minus 1 to the power of 0. This is just equal to 0. So the very first term in this sequence actually vanishes, and that's why I'm allowed to start my infinite sum at n equals 1 instead of at n equals 0. So just quickly before we have another 10-minute break, let's work out the radius of convergence of this Taylor series. I'm going to use that ratio test I just talked to you about. So the ratio test says that if you take a term in the sequence and then divide it by the term that came just before, you look at that new sequence and take limits. Well, what's going on here? Since I'm taking absolute values, I basically just ignore the minus 1s there. On the other hand, I'm looking at the n plus 1 term. That's x minus 1 to the power of n plus 1 divided by n plus 1. So maybe I better write out a bit more carefully what's going on here. I'm looking at x minus 1 to the power of n plus 1 divided by n plus 1 divided by x minus 1 to the power of n divided by n. And when I do that, when I play with my fractions, I end up with that. Now, it turns out that you get some really nice cancellations in here. This particular sequence is exactly equal to the absolute value of x minus 1 times n divided by n plus 1. And you may recall that if you take the limit of this sequence as n goes to infinity, you get, well, this term goes to 1, and this term just stays at the front, x minus 1. Now, the ratio test tells me that in order for this to converge, I really want the absolute value of x minus 1 less than 1. So therefore, 1 is radius of convergence. All right, I'll leave that slide up. This might be a good place for a break. I'll leave it there and I'll see you again in about 10 minutes. Take it easy, everyone. Welcome back, everyone. Hope you enjoyed your brief break. Sorry, excuse me. Okay. Let's get back to our Taylor series. So we just had a look at an example of a computation of Taylor series. We were looking at the Taylor series of the function logarithm of x, the natural logarithm of x, and we were trying to find the Taylor series about the number x equals 1. And we also found that the radius of convergence of this particular Taylor series was 1. Now, I want to take a brief pause and discuss what we just showed. We found the Taylor series. We found that this was the Taylor series. Now remember, this is an infinite sum. And so the question is, does it converge or not? And what we just showed using the ratio test is that this infinite sum converges provided x is between 0 and 2. Now, this is actually all we showed, but I want to point out what else is true, other facts about this particular Taylor series that are true, but don't actually follow immediately from the computation we just did. So we showed that it was convergent for x between 0 and 2. It turns out that it's actually also, this series is actually also convergent when x equals 2. However, this series is not convergent if x equals 0. And there's an easy way of seeing that, because if x equals 0, what you end up with is this sum here, minus 1 to the n minus 1 on n times x minus 1 is minus 1 to the power of n. Now, minus 1 to the power of n times minus 1 to the power of n is just going to be 1. And so what we end up with is this minus 1 to the power of minus 1, which is the same as minus 1 to the power of 1 divided by n. And so this is just minus the sum from n equals 1 to infinity of 1 on n. And we recognize this as the harmonic series, 1 on 1 plus 1 on 2 plus 1 on 3. And so this is divergent. But if instead of 0, we had 2, we would get something which is actually convergent. So this is something we didn't actually show, and I'm not going to prove it for you. I'm just going to state that it is true. Another piece of information that we have, which is not obvious from what we just did, is that not only is this Taylor series convergent, but it does actually equal the original function ln of x that we were dealing with in the first place. And this is because it turns out that the natural logarithm is one of those suitably well-behaved functions. So the natural logarithm does actually equal this infinite sum, at least if we're looking at values of x strictly between 0 and 2, but we do allow x equals 2 as well. So these are things to keep in mind. These are all true things, but proving it is a bit beyond what we'll do in this course. We're just assuming all of our functions are suitably well behaved. We're now going to have a look at some other fairly well-known Taylor series and see if we can calculate the Taylor series for a bunch of well-known functions. Okay. The first of these, the Taylor series of f of x equals e to the x. Pick an arbitrary point A, and you need to calculate the radius of convergence about that particular point A. Now, so remember Taylor series, in order to work out a Taylor series, we have to compute all of the derivatives. But this is something that's really nice about this particular example. All of the derivatives are the same. Because remember, the exponential function has this great property that when you differentiate it, you just get e to the x back. So the first derivative is e to the x, the second derivative is e to the x, and all of the derivatives are e to the x. So that means if we're trying to use this Taylor series expansion, and we have to evaluate the nth derivative of f evaluated at a, we just end up with e to the a. So that's e to the a. but e to the a doesn't depend on n, so we can actually just take it out the front, and what we're left with is x minus a to the n divided by n factorial. So this is actually the infinite sum, which gives us the Taylor series for e to the x. So we've got an infinite sum. Natural question, does it converge or not? Let's again use the ratio test. Now, to use the ratio test, we need to look at these terms here. We need to evaluate this term for n plus 1 and then divide it by the same term for n. So the n plus 1th term is this, and the nth term is x minus a to the n divided by n, just n factorial. Okay, now we're going to use our fraction rules, and what we end up with is that this is actually equal to n factorial times x minus a to the n plus 1 divided by n plus 1 factorial times x minus a to the n. But if we take the absolute value of that, we end up with this particular expression here. Now, we can cancel. This term cancels with that n there, and we're just left with x minus a times n factorial divided by n plus 1 factorial, but you may remember that n factorial divided by n plus 1 factorial is precisely n plus 1. And so we end up with this limit here. But what is really interesting is that this limit is actually 0 no matter what x is. So no matter what x you pick, this series is actually going to converge. Another casual way of saying this is the radius of convergence is infinity. So that's a silly, both correct and that's a correct way of saying it. I guess it's slightly weird to say a radius, which is a real number, is infinity, but you get the idea here. The radius of convergence is infinity. But what's more interesting is not only does this sum actually converge everywhere, but remember the exponential function is one of those sufficiently well-behaved functions. Not only does this infinite sum converge everywhere, but the thing it converges to everywhere is actually e to the x, the original function we're interested in. So maybe this is getting, maybe you don't fully enjoy hearing this, but it is quite nice when a function does actually equal its own Taylor series, because it doesn't always happen. All right, so that was the exponential function. There are some other obvious ones we can look at. The sine function. In fact, let's make this even easier, and let's just have a look at the Maclaurin series of the function f of x. So remember, Maclaurin means Taylor series centered at a equals 0. Also need you to determine its radius of convergence. So, same deal as before. In order to calculate the Taylor series, we have to differentiate. Well, the derivative of sine is cosine. The derivative of cosine is minus sine. The derivative of minus sine is minus cosine, and the derivative of minus cosine is sine. But once we get back to sine, things start repeating again. So we've got a cycle of 4. And so a succinct way of describing what I just described to you is to say the following. Well, we're not doing all the derivatives everywhere. We're just looking at the derivatives at x equals 0. So if we have a look at x equals 0, f of 0 equals sine of 0, which is 0. The first derivative at 0 is just cosine of 0, which is 1. The second derivative is minus sine of 0, which is 0. And the third derivative is minus cosine of 0, which is -1. And then as soon as we get to the fourth derivative, we get back to 0, and then this repeats. So what's really nice is that all of the even derivatives vanish. So the nth derivative of 0 equals 0 if n is actually an even number, which can be expressed as 2m, where m is just some other natural number. On the other hand, if we're dealing with n, which is an odd number, so let's say n is 2m plus 1, then the derivative is either 1 or -1, and there's some more bouncing up and down that has to go on here. So the best way to account for that is to write -1 to the power of m. So this is how it has to go down. So how do we calculate the Taylor series then? Well, we're going to be a little bit tricky in how we do this. Let's just write out the Taylor series. Let's write out the first few terms. So remember, the Taylor series is the derivative evaluated at 0 times x to the power of n divided by n factorial. Let's just write out the first few terms. Well, when n is equal to 0, the zeroth derivative of f evaluated at 0 is 0, so there is no n equals 0 term. On the other hand, the first derivative is 1, and so we get x. There is no n equals 2 term because the even derivatives vanish, but there is an n equals 3 term. This time the derivative is -1, and we've got to divide by 3 factorial. So x cubed on 3 factorial. We keep going like this. We end up with x to the 5 on 5 factorial minus x to the 7 on 7 factorial. So we can keep doing this, but there is a cleaner way of expressing this. What you may notice, you try and write this whole expression here as a new infinite sum and try to make it look as clean as possible. So what's going on here? Well, we're just going to ignore all of the 0 terms. We're not adding them up, so we might as well just ignore them. So what are we adding up then? Well, we're adding up these terms here, because remember, the only things we're adding up are the derivatives. We're adding up over the odd values of n. Odd values of n look like this, 2m plus 1, for m being a positive integer. The derivative in that case looks like -1 to the power of m. Now, if we're picking up that particular n term, we've got to go x to the power of n, which we've said is 2m plus 1, and divide by n factorial. We've said that n is 2m plus 1, so that's 2m plus 1 factorial. So perhaps a cleverer way of writing this Taylor series is like this. The Maclaurin series for this function sine of x is equal to the sum. I've made a typo again. This should be summing from m equals 0 to infinity, not n. So the sum from m equals 0 all the way up to infinity of -1 to the power of m times x to the power of 2m plus 1 divided by 2m plus 1 factorial. All right. So this is the Maclaurin series itself, but it's an infinite series. We need to determine if and when this Maclaurin series, this infinite series, is actually going to converge. Well, I'm not going to do all the details. I might leave it to you. But if you look at the m plus 1 divided by m term, what you'll end up with is exactly this expression here. And it turns out that this limit, once again, I made a typo, this should be limit as m approaches infinity, not n. The limit of this expression as m goes to infinity is 0 no matter what x is. And so that means we get convergence everywhere. And we also find that the radius of convergence is infinity. But perhaps even more importantly, not only does this function converge, not only does this series, this infinite sum converge everywhere, but it does actually converge to the function sine of x. So that really is what you want. So yes, another example of a function that does equal its own Taylor series. So what is so important about all of this? What I consider to be so important about this is that these are all examples of functions that come up a lot in real life. And what I've just given you, these are the tools that you can use to actually work with these functions. Because the sine and cosine functions, they're rather hard to describe, but here is a concrete way of actually describing them. We've given you great ways of approximating these functions. So if you're given a question in real life where you have to compute things using sine and cosine, you can actually do it via the Taylor series instead. So that's pretty nice. Now, Taylor series can actually be done in Mathematica. So let's have a look. How would you do this in Mathematica? You do it with these sorts of commands. You use the series commands. This is the command that turns a given function into an infinite sum. You've got to feed it the function that you're interested, whose Taylor series you want to find. You have to tell the function what variable you're breaking up the Taylor series into. Again, remember, you might have a function that's defined to have more than one variable, but you might not want to take a Taylor series in one of the variables. You need to specify which variable you're doing it about. You've got to specify the point about which you're taking the Taylor series. And finally, you also have to tell it how many terms of the Taylor series you want it to give you. Because, you know, you can't put infinity in there. Infinity, you can't tell a computer to give you infinitely many terms. So I've told it to give me 10, and this is what I end up with. 1 minus x squared on 2 plus blah, blah, blah. Plus this is basically the error term. What this means, strictly speaking, is that O of x to the 11 is actually bounded by x to the power of 11, or at least by some constant times x to the power of 11. Exactly what this means, you don't need to worry too much, but what you need to know is that this is the error term. This is Mathematica telling you, I've given you the first 10 terms of the series, but there are others out there. They're not too important, but there are others out there. So this is what happens if you tell Mathematica to give you 10 terms of this Taylor series. Now, as I said before, you can't tell Mathematica to give you the whole infinite sum. I tried doing that just for fun to see what would happen. Well, obviously Mathematica is not going to be fooled. You're supposed to put an integer in there. Infinity is not a machine-sized integer. So that was a bit of fun. Okay. So because it doesn't want to do that, the output of that particular command was just the same as the input. Okay, well, I've done 10. I've done infinity. It didn't like that. Maybe there's another large number I can try. Yes, Mathematica will do it, but it's not going to be happy about it. It's going to tell you that there are a lot of terms missing in there. So that's fine. So this is how you can do a Taylor series in Mathematica. Now, what's interesting about Taylor series is that you can actually do Taylor series for functions of more than one variable. So here, as a nice segue into the next, as a nice segue into the next section, I gave Mathematica a function of 2 variables. I gave it a function of both x and y. And I told Mathematica that I actually want a Taylor series in both of the variables. I'm going to do it about x equals 200. I'm going to do it about y equals 400. And I'm only going to do to order 1 in both variables. What is that going to be? And Mathematica gives you the expression here. So that's quite nice. Okay. So any questions on Taylor series there before we move on to multivariable functions? All right, let's move on to multivariable functions. Okay. Let's suppose that now we've got a function of two variables. Now, a lot of this theory is actually generalizable to any number of variables, but for the moment, we'll just stick with two variables so I can actually write all the formulas down. Like we had a linear approximation for functions of one variable, we also have a linear approximation for functions of two variables. This time, you've got to take two different derivatives. You've got to take the derivative of the function with respect to x. So this is what I mean by that, the derivative of f with respect to x, and this partial, this symbol here is just a del, I think. It's basically what you use instead of the d on dx if you're dealing with multiple variables. So take the derivative of f with respect to x, calculate the derivative of f with respect to y, evaluate it at the point you're interested in, then add the derivative of f with respect to x at that point, multiplied by the change in x that you're looking at, and then multiply by the change in y that you're looking at. Now, I promise I'll get you a picture of what this looks like briefly, but in the same way that the linear approximation gave you a tangent line to a function, this is meant to be giving you a tangent plane. This linear approximation, you take a graph, a multivariable function graph, and you pick a point and you take the tangent plane to that point. And that's exactly what this expression is meant to be giving you. And the tangent plane is called the linear approximation for that function at that particular point. And as we saw with the single variable case, we actually expect this approximation to be good, at least if your function is well behaved and if you're dealing with values of x and y, which are sufficiently close to this point A, B. Okay, let's have a look at an example so we can see this working, how this tangent plane idea actually works. Let's say that I've got a region in XY space, and let's say that the temperature of that region is given by 100 minus x squared minus y squared. I didn't specify units, but let's just ignore units for the moment. Okay. Now, in order to calculate the linear approximation, we need to calculate the first derivatives. The first derivatives of this function with respect to both x and y. Well, using our rules, if we differentiate with respect to x, that doesn't depend on x, the 100 doesn't depend on x, the y squared doesn't depend on x, and the minus x squared just becomes a minus 2x. On the other hand, if we differentiate with respect to y, this term vanishes, but this term just becomes minus 2y. Okay, now what I'm going to do in this question is find the linear approximation for t about the point xy equals 0, 5. So what is this going to look like? Well, remember, our definition of linear approximation is as follows. We've got to evaluate the function at the point of interest. We've got to evaluate the partial derivatives at the point of interest. And we've got to multiply these partial derivatives by the difference of the corresponding point from the reference point. I did that wrong. 0 is the x reference point and 5 is the y reference point. So I've got to I've now got the function and I've now got its two partial derivatives. I just need to evaluate all of those functions at the point 0, 5, and I'll have my approximation. Well, if I just chuck 0, 5 into here, I get 75. The derivative in the x direction at the point 0.05 is just 0, and the derivative in the y direction is minus 10. So my linear approximation is exactly this. I don't have any x terms because the derivative in the x direction was just 0. So I end up with this here. Now, as I said before, this is the equation of the tangent plane. So let's have a picture of what this actually looks like. This is the tangent plane. So that means it's meant to be a good approximation for this function, at least if x, y are close to 0.5. And here's a picture of the actual tangent plane. So this guy here is just t of x, y. This is the graph of that function. And this plane over here is the tangent plane. So this is what linear approximations look like, at least for functions of two variables. So let's keep going with these sorts of approximations. Are there any questions at this point before I move on to some more examples? All right, let's have a look at our next example. So this time we're going to be looking at a function of two variables, and the function is f of xy is equal to e to the minus x squared times sine of y. Now I want to find the tangent plane of this function at the point x equals 1 and y equals pi on 2. Now, another thing that I want us to do in this question is find an approximate value for e to the minus 0.9 squared times sine of 1.5. This is one of the powerful things that Taylor series can give you. Because if you didn't have a calculator and I asked you to work out what e to the minus 0.9 squared sine of 1.5 was, I suspect you wouldn't really be able to give me a clean answer. But it's through the power of Taylor series that we can actually find a rather clean answer to this question. So let's see how that works out. In order to find the tangent plane, we have to take the derivatives. Let's differentiate with respect to x first. Well, we know how to differentiate the exponential function. That's just the exponential function times the derivative of what's inside, minus 2x times e to the minus x squared. Sine of y is just a constant, so that comes out the front. Similarly, if we differentiate with respect to y, the e to the x squared comes out the front, but the sine of y becomes a cosine y, because the derivative of sine x is just cosine x, so the derivative of sine y is cosine y. Okay. We now have enough information to calculate the linear approximation. So remember, this is f. In order to find the linear approximation, you've got to evaluate the function at the point in question. If x equals 1 and y equals pi on 2, then f of xy is equal to e to the minus 1 squared times sine of pi on 2. But e to the minus 1 is just 1 divided by e, and sine of pi on 2, well, we know that's equal to 1. So that's just 1 on e there. What next? Well, we've got the term, we've got to differentiate the function of value with respect to x, evaluated at the point 1 comma pi on 2, and we've got to look at x minus the reference point for x. But similarly as before, the derivative of f with respect to x is exactly this. If I plug in x equals 1 here and y equals pi on 2, what I end up with this time is minus 2 divided by e. Now, if I differentiate with respect to y and evaluate that y equals pi on 2, cosine of pi on 2 is 0, so this y term vanishes. And the approximation I'm left with is that one there. So this is quite nice. Now what? Well, that wasn't, this is the tangent plane. But the question also asks us to evaluate this, or at least approximate that particular value there. Let's do that. E to the minus 0.9 squared times sine of 1.5. That is the same as the function f evaluated with x equals 0.9 and y equals 0.5. But I have an approximation for this function. It's this one up here. 1 on e minus 2 times x minus 1. Well, I said x is 0.9. So 0.9 minus 1 divided by e, that's about the same as 1.2 divided by e. This is probably a pretty good approximation for the value of e to the minus 0.9 squared times sine of 1.5. This is what makes Taylor's series so powerful. And down here, we've got a graphical representation of what's going on. The orange is really the function f of x, y, and this guy here is the tangent plane. So that's great. So we've now had a look at linear approximations. Now I want to spend a bit more time talking about what these linear approximations actually tell us. Now, there is a nice way of thinking about tangent planes here. And we think about it in terms of how much the function changes if I change x a small amount and if I change y a small amount. So the formula for linear approximations can basically be interpreted this way. Let's try and make that a bit more precise. Let's say that I take my linear approximation to the function f at a particular point, then I just rearrange slightly to get this particular expression here. Now, this is where the changes in changes comes from. This left-hand side is change in f. X minus a is change in a. Sorry, change in x. And this y minus b is a small change in y. So roughly what this is saying is that if you move x and y a small amount, then you can use the linear approximation to work out how much f is going to change. So if we make this really hand-wavy and take limits and talk about infinitesimal things, what this ends up being is a small change in f is going to be the same as, sorry, if you move x and y by a small amount, the change in f can be approximated by the derivative of f with respect to x times the small change in x, plus the derivative of f with respect to y times the small change in y. It's now that we take limits to get this equation, which I can appreciate might not mean a huge amount to you, but nevertheless, this is what we write. Infinitesimally, we take limits, an infinitesimal change in f arises as f of x times an infinitesimal change in x, plus the derivative of f with respect to y times an infinitesimal change in y. This formula actually comes up a lot in mathematics because this is a situation in which we can work out if we've got a function and we don't really know exactly what it is, but we know how much its inputs are changing, and we know the derivative of the function at a particular point, then we can use it to work out how much the original function is changing as well. So let's have a look at an example of this in practice. In electrical engineering, you'll come across power, resistance, and voltage fairly often. There's a well-known formula that tells you that if you've got E as a particular voltage and you've got R as the resistance, then the amount of power that's coming from that is given by this particular formula here. The power as a function of voltage and resistance is given by E squared divided by R. So in this question, we're being asked to find a linear approximation for power for values of the voltage close to 200 and values of the resistance close to 400. Hence, use this linear approximation to find how much the power is going to change if you change E and R slightly. Okay, linear approximation. That means we have to calculate the derivative of P with respect to these different variables. So if we differentiate P with respect to E, well, the derivative of E squared is just 2 times E, and that R goes down the bottom as usual. The derivative of E with respect to R, well, the derivative of 1 on R with respect to R is, using the well-known power rule, just minus 1 on R squared. So that's the computation of those derivatives. What next? Well, we need to evaluate these derivatives at the points of interest. E equals 200 and R equals 400. Well, if you evaluate the function the derivative of P with respect to E evaluated at the points 200, 400 is exactly equal to 2 times 200 divided by 400. But of course, that's exactly equal to 1. And over here, we're trying to evaluate the derivative of P with respect to R at the points 200, 400. But that's exactly equal to minus 200 squared divided by 400 squared. That turns out to be exactly a quarter, minus a quarter. So this is our linear approximation here. Now this isn't quite, well, the question also asks us to use this to find the effects that a change in E and R has on P. This linear approximation is basically it, but using the notation we found in the previous slide, we have this sort of more correct formula here. A small change in P is equal to a small change in E, because there's a 1 there, minus a small change in R, because of that quarter there. So this is in practice how you can simply use linear approximations to see how much a particular quantity is changing if you know by how much its dependent variables are changing by, its independent variables are changing by. Why would you want to do this? Well, maybe you just hate dividing by things. Maybe you hate squaring things. So instead, you just do it this way instead. So this is how you would do that. Now, the next example is a bit of a fun one in that it's all just pictures and I'm not really asking you to compute anything. We've got, this is pretty interesting, I think. We've basically got this apple here and we're plotting it on the X and Y axis. And for each point on this apple, we associate to that point a value. That value basically determines its color. And so this is really what's going on here. These bits up here, basically where the background is just white, but this in here is the actual apple. And you can see that the values are changing a bit because the color that we see here does actually change a bit depending on where we are. Now, of course, maybe you don't want to deal with this function straight up. Instead, you want to assume that it's got a good linear approximation, and you hope that the tangent plane that you find does actually give you a good approximation to the color. So these are considerations that are actually used in computer graphics more often than not. Colors are given numbers, and as soon as you're given numbers, you're given functions, and you have tangent planes to deal with. You might find them helpful when you're doing graphical analysis of something. Now, one other great application of this linear approximation that we can do is the idea of errors. This is something that comes up a lot in data science. So the rough situation that we're dealing with is as follows. Let's suppose that we've got a function f of xy, and let's suppose that we know what the function is, but let's say that we're trying to evaluate the function at a particular point xy, and we don't know what the xy point is. How can we proceed? Well, just by itself, we can't do anything, but if we happen to know that the x value is close to a, let's say that it's within E1 of a, and let's say also that the value of y is close to b, in fact, let's say within a distance of E2 of b, then we might actually be able to say something. Because we'd like to hope that in such a situation, the value of f of xy would be close to f of ab. But now the question is how close? And this is something we can again achieve by looking at linear approximations. Using this linear approximation formula, we can turn this into an error formula. The amount E by which f of xy differs from f of ab, this should approximately be equal to the absolute value of the derivative of x evaluated at that point times the error in the x value, times the absolute value of the derivative of f in the y variable multiplied by the error in the y value. So this could actually come in quite handy, because this actually gives us a way to work out how much error we're going to be introducing in a given system. So let's get on with an example of this. Let's suppose that we're making metal barrels. Let's say that we're asking that the radius of the base of this barrel is 1 meter, and let's suppose that its height is 2 meters. Now let's suppose that, well, we can't, it's basically impossible to get something that's exactly 1 meter. So let's suppose that we're allowing for a 5% error in the construction of the radius, and let's suppose we're allowing the same error in the height. What is the worst case error for the volume that we would expect in this situation? Well, linear approximations. But before we get into the linear approximations, we have to remember that the linear approximation formula, the error formula that we had on the previous slide, it only really applies to absolute errors. And in this question, we're only given relative errors. So the first thing we need to do is convert our relative errors to absolute errors. This is a fairly straightforward computation. A 5% error, well, that's at 0.05 meters of the radius, because remember, for the radius, it's 5% of 1 meter. On the other hand, a 5% error in a height of 2 meters, that could be as bad as 0.1 meters. Okay, well, what are we trying to do? Errors in the volume. The volume has this, I'm sure you might all be aware of the volume of a cylinder, which is pi times the radius of the base. Pi r squared gives you the radius of the base of the circle. And then you need to multiply by the height. Okay, so that's the volume. We're looking at errors for the volume. That means we need to compute derivatives. The derivative of the volume with respect to the radius is, well, dv on dr is equal to 2 pi rh. Remember, the derivative of r squared with respect to r is just 2 times r. But if we evaluate at 1, 2, what we end up with is 4 pi. A similar computation will give you that the derivative of v with respect to h at the point 1, 2 is just pi. This is enough information to give us our error formula. Error is going to be 4 pi times the error in the r component plus the derivative in the h component times the error in the h component. So this gives us an absolute error of about 0.3 pi. Now, this is an absolute error. The question was originally phrased in terms of relative error, so it would be good manners to convert it back to relative error. Now, the volume of a cylinder with radius 1 and height 2 is exactly equal to 2 pi. And so that means the relative error is going to be 0.3 pi divided by 2 pi. That's exactly equal to 0.15, which is 15%. So that is that. That almost brings us to the end of Unit 8 as well as Unit 7 this evening. Now, the one thing I want to leave you with is an application which sort of combines these Taylor series with the optimization theory we saw last lecture. Well, actually, earlier this evening. Optimization via quadratic functions. So this is another way we can numerically try to optimize a function. So let's say you've got a function f of x. Let's say we're trying to find a maximum value of this function f of x. Most of these numerical algorithms will require you to choose an initial guess that you think might be good for a good initial guess for the location of the maximum. Now, we're going to try and optimize this via quadratics. Why quadratics? Well, the reason is that quadratics are actually the simplest things to maximize. If I told you I was going to write an exam and I told you I was going to give you a function that I want you to maximize, and I told you that you could choose what the function is to maximize, you would always choose a quadratic because it's the easiest thing to optimize. Simplest function to optimize. Okay, so we take an initial guess. Now, how are we going to proceed? We actually use Taylor series. We use the second order Taylor series approximation for this function. Because if we've picked a point, then roughly speaking, f of x should approximately be the value of the function at that point, plus the tangent line term, plus the second order term, which is the second derivative of f divided by 2 times the square of the distance. So if we're close to the point xi, then f of x should, roughly speaking, look like this. Now, the thing is, we know how to find the maximum of that. At least if the second derivative of this quadratic is negative, we know it's going to have a maximum somewhere. And so let's just choose that to be the new point. So the algorithm is you pick an initial point, find a quadratic approximation for that function relative to that point. That if the second derivative at that point is negative, then this new quadratic approximation you've constructed should actually be a maximum. And so let's just travel there to get your new maximum. So if that's x naught, you'd find your second order Taylor series approximation. And then this would be your new point x1. But then you do the exact same thing. You pick another second order approximation and hopefully move over to the next point, x2. You would just keep doing this, and hopefully, if you continue to have second derivatives which are negative, hopefully you will actually arrive at a solution, or at least get arbitrarily close to the solution that you desire. Okay, we'll leave it there, guys. We've now done section 7 and 8, and you now have enough information to do your assignment. So I'll leave the lecture there. Thanks very much for attending. And as usual, please feel free to stick around and ask questions if you would like.